So in the last class, we spoke about uh, the idea of an instantaneous unit hydrograph. So let me again probably restate some of the fundamental theory behind it. So the idea, see, so far we've been talking about, whenever we spoke about the unit hydrograph, we spoke about it in the context of uh, a given duration, right? So we said a 2-hour unit hydrograph or a 4-hour unit hydrograph and so on. What we meant by those terminology was that any given unit hydrograph for a given catchment or a given watershed has a correspondence to the duration of the rainfall event, right? So if I have, for instance, a 2-hour unit hydrograph, that corresponds to an excess rainfall event of 1 centimeter happening over a duration of 2 hours, right? So, and then of course we spoke about how to get multiple durations. If I want a 4-hour unit hydrograph from a 2-hour unit hydrograph, how to do that? If I want a 1-hour unit hydrograph from a 2-hour unit hydrograph, and so on. We've discussed all of that in great detail. So now the very final thing that we're going to talk about is this idea of an instantaneous unit hydrograph, right? So as you can imagine, whenever we spoke about unit hydrograph, we associated a time duration with it, right? 1 hour, 2 hour, 4 hour, whatever it may be. So here we are talking about an instantaneous unit hydrograph, which means that I receive the excess rainfall of 1 centimeter, but it happens in such a quick duration, or it happens so fast that effectively you can just call it an instantaneous unit hydrograph, right? So this is the limiting case of my d-hour unit hydrograph when d tends to 0. So that's the understanding behind this idea of a unit hydrograph. Now, as you can imagine, it's impossible that you get 1 centimeter of excess rain in 0 time, or or in very shorter time. So you can think about it like maybe a small duration, let's say 5 minutes or 10 minutes, maybe 20 minutes. And that kind of a duration is what we're talking about. When we say 0, we don't actually mean 0. It's something approaching 0. All right. So naturally, this whole concept is kind of it's an imaginary idea, but it's helpful sometimes. When would it be helpful? Suppose I receive rainfall whose intensity is changing as a function of time. Almost every, let's say, every 10 minutes, the rainfall intensity is changing. You might have experienced this, right? Rainfall intensity does not remain constant for a long time. So typically, when rainfall data is collected, it is collected in, let us say, 15-minute intervals, right? Because it's assumed that within 15 minutes, more or less, the rainfall intensity is assumed to be about uniform. So when we collect rainfall data also, we try to collect it at a 15-minute interval, for example. So you can imagine that. Suppose I have data where the rainfall intensity is changing every 15 minutes, right? So then you can't use your unit hydrograph approach, right? 1 hour, 2 hour unit hydrograph will not apply to a situation where I have rainfall intensity changing every 15 minutes or every 10 minutes, whatever it may be, right? So in those cases, you need a finer unit hydrograph of finer duration. So effectively, we just call it instantaneous. All right. So then if I have, so what you see over here is the rainfall intensity changing as a function of time, right? So then if I have an instantaneous unit hydrograph for every instant in time, I can simply take that, multiply it by the unit hydrograph, then go to the next time step, which is some time delta t away, do the same thing, and then sum them all up. Then I get the flood hydrograph for that situation. All right. So that is the fundamental idea of a instantaneous unit hydrograph. And now we are going to look at how to obtain an instantaneous unit hydrograph given a d-hour unit hydrograph. Okay. So let's just imagine this. So consider that I have an S curve from a d-hour unit hydrograph. Okay. So let me just draw this over here. Okay. So let me some of the space at the top. Okay. So I have time on the x-axis, q on the y-axis. So let's say the S curve looks something like this, right? So this is the S curve corresponding to some d hour unit hydrograph, right? So let's say this is S1, okay, and naturally this is, yeah, extend a little bit more. So this is due to rainfall intensity. So what will be the rainfall intensity of this unit of this S curve? I'm sorry. What will be the rainfall intensity? Anybody?
1 by D.
Yes, 1 by d centimeters per hour, right? So the rainfall intensity here, so I, let me say over here, I equal to 1 by d centimeters per hour. Okay, so you just keep that in mind. Okay, I'm going to erase this off because I need this space. All right. So then I have this S curve arising out of this rainfall intensity of 1 by d centimeters per hour. Why is it 1 by d? Because it is 1 centimeter of rain in d hours imposed indefinitely. So therefore, the rainfall intensity is 1 by d centimeters per hour. So, sorry, the effective rainfall intensity is 1 by d centimeter. It's not the rainfall intensity, it's the effective rainfall. So when I say effective rainfall, I mean the runoff, right? Okay, so the effective rainfall intensity is 1 by d centimeters per hour. I equal to 1 by d centimeters per hour. Now I will take another S curve, the same S curve, I will lag it by some small duration dt, and then I get this. Okay, let us say this S curve is S2. Okay, so I lag another S curve by some time interval dt. So this time between these two S curves is dt. So over here, I will draw another effective rainfall intensity of, the intensity is the same, everything is the same. I just lag it by some duration dt, right? So now if I take the difference between S1 and S2, right? So if I do S1 minus S2, what will I get? S1 minus S2 will give me a direct runoff hydrograph. Sorry. So if I do S1 minus S2, it will be a direct runoff hydrograph produced by how many centimeters of rainfall? Can you quickly calculate?
By D.
What is that?
dt by D.
dt by d. Does everybody agree with that? dt by d hours. Sorry, dt by d centimeters. Right? dt multiplied by 1 by d. dt hours multiplied by 1 by d centimeters per hour. So it will be produced by dt by d centimeters. Does everybody agree with this? When I do S1 minus S2, it will give me a direct runoff hydrograph produced by dt by d centimeters of excess rainfall, correct? Right. So then, if I take this S1 minus S2 and divide it by dt by d, what will I get? I will get a unit hydrograph of duration
dt.
dt, right? So that's all I'm doing. I'm taking my S curve, lagging it by some duration dt, subtracting the two S curves, S1 minus S2. I get a direct runoff hydrograph of some effective rainfall depth. I divide by that depth, I obtain the unit hydrograph of that duration equal to dt, right? So let me, if I want to write it mathematically, so this unit hydrograph that I've obtained, this unit hydrograph, let us say, is a function of t, is simply S1 minus S2 divided by dt. This 1 by d, I will write it as I, okay? Over here, I have a 1 by d, right? I'll just write it as I times dt. That's all, okay? We all agree that 1 by d is I. So I'm just writing it like this. So now, what is the definition of the instantaneous unit hydrograph? This is the unit hydrograph that I'm getting by lagging it by some time delta t. Now, if this delta t tends to 0, then my IUH, instantaneous unit hydrograph, will simply be limit dt tending to 0 s1 minus s2 I dt, which will be 1 by I ds by dt, isn't it? Right? The slope of my S curve divided by I, the rainfall intensity, the effective rainfall intensity, will give me my instantaneous unit hydrograph. If I assume, uh, 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 that my dt is tending to 0, then that gives me my instantaneous unit hydrograph. It's fairly straightforward. Okay, and then of course the special case of this is yes. Is there a question? Are you
No, sir, no, sir.
okay? Right. Now the special case of this is if the original S curve that I considered was a 1 hour unit hydrograph. If I consider a 1 hour unit hydrograph, what happens to I? I will be I will be
One.
I will be 1, right? So if I consider a 1 hour unit hydrograph, then it will simply be ds by dt, right? Is that okay? So the procedure is exactly the same as whatever we have discussed so far in terms of how to obtain the unit hydrograph, right? So the instantaneous unit hydrograph. So the approach that we will use is exactly the same as that, right? So now from this instantaneous unit hydrograph, you can also derive uh, uh, the higher uh, d hour unit hydrograph. So this was how I obtain an instantaneous unit hydrograph given a d hour unit hydrograph. Using a similar approach, you can derive the d hour unit hydrograph given an instantaneous unit hydrograph, right? So I'll leave that the mathematics to you. Anyway, it's also available in the textbook. You can read about it. It's fairly straightforward. Okay. So now what I'm going to do is we are going to do a quick recap of whatever we have learned so far in the unit hydrograph approach, right? Because uh, what I'll do is that I'm going to share a list of problems, right? That will cover the entire, concept of unit hydrograph, all these different types of approaches that we've used in the unit hydrograph approach. I'll give a bunch of problems which will cover almost every aspect of these, and I want you to solve those and be familiarized with these different kinds of problems. Okay, we have taken so many different approaches of using the unit hydrograph theory. Okay, so let's do a recap, and then I'll share the sets with you. Okay, so let's quickly look at what we have learned. The very first thing that we learned in the unit hydrograph approach is that this idea of using a linear theory, which means a linear way of understanding a watershed, right? We assume that the watershed behaves as a linear system, by which I mean that if I know the input and the output for a unit input, then for any other input, I can find what the output will be, right? So that's what this linear theory means. So therefore, we come up with the notion of the principle of proportionality and the principle of superposition, right? Proportionality means if I know the response for a unit input, then I know the response for any other input. And the superposition means if I have two events separated by some time duration, you can add the responses of those two by lagging them by the appropriate time duration, and the summation of those two responses will give the overall response of the system, right? So that's what these two principles are: proportionality and superposition. So that's the very first thing that we learned, and then of course we applied this in so many different ways. The next thing we did was, given a unit hydrograph, right? If you go back and look at our previous lectures, you will find out that this is the exact sequence in which we went through the whole unit hydrograph concept. First, I said, I will give you a unit hydrograph and ask you to estimate the response to some given rainfall event, right? I would say, okay, so this is the unit hydrograph for a 4 hour, this is the 4 hour unit hydrograph of a given catchment. This particular catchment received 3 centimeters of rainfall in the first 4 hours and 4 centimeters in the next 4 hours. What will be the flood hydrograph? Something like that would have been asked, right? in this you can have so many variations of this. I can either give you the actual rainfall and the fee index and ask you to find out the effective rainfall, or I can directly give you the effective rainfall and ask you to find out the flood hydrograph, right? So within this there are variations, right? When I say a response to rainfall event, it could be I could directly give you the rainfall amounts and the fee index and ask you to find the effective rainfall. Okay, and then I can give you base flow, and then you will add all of them and you will get the flood hydrograph, right? So this flood hydrograph, remember, is composed of the direct runoff hydrograph and the base flow, right? So this is the first kind of problem that we looked at. Given a unit hydrograph, estimate the response to some rainfall event, which again I can divide into uh, a rainfall hydrograph or an effective rainfall hydrograph. Both of these possibilities are there, right? So this is the first class of problems that we looked at, how to use the unit hydrograph approach. The second one was how to derive a unit hydrograph given a response to some rainfall event, right? So the first problem was given unit hydrograph, how to find the response to rainfall event. The second one that we looked at was given a response to a rainfall event, how to find out what the unit hydrograph is. And even within this, we had like multiple approaches. How to do it for isolated storms versus complex storms, right? If you remember, that's the sequence in which we went. First one was if I give you an isolated storm of, let us say, 2 hours duration, so much runoff was received. So from that runoff, you would estimate how much effective rainfall depth has happened. From that effective rainfall depth, you would find out what the unit hydrograph would be. So that is how you would deal with an isolated storm or an isolated rainfall event. And the other one is a complex storm where I have multiple events, rainfall events of varying rainfall amounts, right? So I could have 2 centimeters in the first D hours and 3 centimeters in the next D hours and so on. That's a complex rainfall event, right? So how to derive the unit hydrograph if I give you this kind of a complex storm event, right? So that's the next thing that we looked at, right? Then the next problem that we looked at was the approach of using a given D hour unit hydrograph and finding out what unit hydrograph of different durations, right? I would give you a 4-hour unit hydrograph and ask you to find out an 8-hour unit hydrograph or a 12-hour unit hydrograph, right? So if I give you a 4-hour unit hydrograph and ask you to find an 8-hour unit hydrograph or a 12-hour unit hydrograph, what approach will you use? Anybody remembers?
Superposition.
The method of superposition, right? Why are we using superposition, Ajay?
It is multiple of 4.
Yeah, it's an integer multiple of the given D hour unit hydrograph, right? So this is twice 4, this is 3 times 4, and so on. So it's all fairly straightforward, right? So whenever you are given a D hour unit hydrograph and you're expected to find an integer multiple of that, a unit hydrograph of duration, which is an integer multiple of your D hour, you use the method of superposition. If you are asked to estimate a storm which is or a unit hydrograph which is not of an integer multiple. So for instance, if I give you a 4-hour unit hydrograph and I ask you to find a 2-hour unit hydrograph, right, or a 1-hour unit hydrograph, right? So if you're asked to do one of these, then you can't use the method of superposition. Then you use the S-curve method, right? See, for 8-hour and 12-hour, S-curve can also be used. S-curve is a general method which is applicable for almost any duration, right? But the method of superposition only works when it's a integer multiple, right? So that's the only distinction between these two methods. Fairly straightforward, right? There's nothing complex or complicated about this. As soon as you understand the linear system assumption, once that is clear, all of these different approaches that we are taking, they're all very straightforward. There's no complicated logic or whatever, right? Okay, so then that's next uh, problem that we solved. Then the next thing that we did was looking at these synthetic unit hydrographs, right? We looked at the Snyder unit hydrograph, the SCS dimensionless unit hydrograph, or the SCS triangular unit hydrograph, and so on, right? What is the purpose of the synthetic unit hydrograph? Does anybody remember? What is the purpose of a synthetic unit hydrograph?
In case if we don't have available data,
Available data of what?
if we don't have details of the unit hydrograph of
Okay,
a catchment.
okay, yeah. So suppose, so the idea of a synthetic unit hydrograph is that if I don't have detailed information, look, so to derive a unit hydrograph, you require detailed information, right? So if I'm able to come up with some empirical relationship between the watershed characteristics and the response of the watershed to a given rainfall event, right? Then I may be able to derive some relationships between the catchment characteristics and the expected response to a rainfall event, right? So I can say, okay, if the size of the catchment is so and so, and if the slope of the catchment is so and so, then this is the kind of time of concentration that you may expect, right? You can use all of those approaches to estimate the base lag, sorry, the base time of the catchment, or the basin lag, or the time to peak, or the typical duration of your effective rainfall, and so on, right? So the synthetic unit hydrograph gives you the ability to be able to come up with an empirical approach towards deriving relationships between a watershed's characteristics in terms of its land use, in terms of its slope, in terms of its soil, and so on and so forth, in and relate that to the response of the watershed to a given rainfall event. So that is the idea of the synthetic unit hydrograph. Okay, and then finally, just today we spoke about it, and in the last class we spoke about the idea of the instantaneous unit hydrograph, which again we used the S-curve method to estimate, right? So the S-curve method, again, we found the application for it in the instantaneous unit hydrograph. So this is the overall, you know, kind of, if you think of the unit hydrograph as a chapter in your in this course, and these are all the things that we have done throughout this semester in the unit hydrograph approach, right? So what I will do is I will share a bunch of problems, maybe about 10 or so problems, maybe more. Okay, so I'll share a number of these problems, which will address each of these issues. Okay, I want you to try to solve all of these problems. Okay, I'm not expecting you to submit them or anything. Okay, this is just for you to solve and get very familiarized with these approaches, because inherently there is nothing complicated about these about the theory or the approach. It is only a question of keeping track of the different processes that you're looking at, right? So as long as you keep everything as long as you understand all of these concepts, there's nothing fundamentally difficult about it that requires a great deal of understanding and so on, right? So that is what I'm planning to do now. I'll share those problem statements maybe later today. Okay. So then, okay. So we have come to the end of this chapter. Now I'm going to spend the rest of the time talking about the next project that we are going to that I'm expecting you to work on. Now, this particular project that we are going to do will involve a significant amount of the use of QGIS, right? If you remember, in the earlier project, you had used what was that, the Thyssen polygon approach in QGIS for estimating average rainfall and so on. So this particular project will be more to do with looking at runoff and trying to come up with an estimate of runoff in a given area. Okay, so maybe I will. Okay, one second. I'll just insert one slide over here and explain what exactly. Okay, my screen sharing is stopped. Let me get back to that. Okay, are you able to see my screen?
Yes, sir.
Okay, good. So now, this third mini project is about estimating. So I'll explain it briefly on PowerPoint, and then I'll take you into the QGIS environment because I want to explain a bunch of things over there. Okay. So the problem statement is simple like this. Okay. So we will imagine that just like we have our IIT Tirupati campus coming up here, college campus is coming up. Let's say in some part of AP. You are free to pick any part of Andhra Pradesh. So college campus is coming up. So when I say college campus is coming up, think of it like like an IIT or so on. Okay. So does anybody know how large our campus is? Any idea what the size of our campus is?
And
549 acres.
549 acres.
Please watch Professor Satya's presentation, I suppose. Okay, 549. If I remember correctly, it's 548, but anyway, that's okay. So about 500 and odd acres. So what you will be doing is whichever district you are in, wherever you want to build this new college campus, you are going to come up with a college a campus of about this size, 500 acres, 550 acres, whatever it is. Okay. So you will come up with a campus of this size. Now the objective for us is within this campus, right? There's going to be buildings coming up, all of that coming up, and then there will be roads and so on, right? So now, in order to ensure that your campus doesn't get flooded when there's a rainfall event, you will require some kind of drainage, sewage system or sewerage system along the sides of the roads, right? So if you imagine, if you remember in last semester, we learned about how to design these, uh, these open channels, given the flow, given the discharge, right? So let us say I have my road over here. On the side of the road, I may have these kinds of drains. So let's say this is my road. So I'm just exaggerating a little bit, but let's assume I have this kind of a drain on both sides of the road, where the runoff will, the runoff from the not only from the road, but also from the other parts of the campus will collect in these side drains, and it will flow off downstream to the outlet of the campus, wherever the campus outlet is, right? Now these side drains need to be designed, right? These side drains need to be designed. Now, what is the basis for designing these side drains? What's the basis for designing these side drains?
Estimate the flood.
No. When you say estimate the flood, what do you mean by that?
Peak value.
Value of what?
Peak runoff. Peak.
The peak runoff, right? So you need, answer is there sitting right on front of your screen. So if you know that what is the peak runoff that this area will experience, right? What is the peak runoff that this area will experience? Then you can design your drain appropriately. I don't want you to design the drain. I want you to find out what the peak runoff for this area will be, wherever you put up your campus. Okay. So your campus could be in any district of Andhra Pradesh. And as you know, the rainfall varies from region to region. If you're in Chittoor, depending on which part of Chittoor you are in, you will get a certain amount of rainfall. So you already have rainfall for that year 2018 that I shared with you earlier during the semester, right? So that precipitation data you already have. Okay, but that is for a given year. Okay, we will assume that given year represents the worst year. Let us say it's the worst year. Okay, or if you find out that rainfall is not appropriate, you can multiply it by some factor and say, you know what, maybe in a different year you may get a larger amount of rain. Okay, so all you know is So given the precipitation data, you can find out what the maximum precipitation that this region will receive wherever you locate your campus. Right? If you locate it in Anantapur district, you know what the precipitation for Anantapur district is. If you locate it somewhere else, you know what the precipitation for that region is. But is knowing the precipitation data enough to estimate the runoff? Or is it not enough? So when I say peak runoff, what are all the factors on which this peak runoff depends? Can anybody name? Okay, I'm going to write rainfall. Can you tell me some other parameters on which this peak runoff depends?
Slope.
Yes.
Catchment.
What is that?
Slopes.
I'm not able to hear it clearly.
Slope.
Slope. Okay. Very good. Slope is fine. Then anything else? Somebody else?
Infiltration.
Infiltration.
Soil type.
Soil type.
Substance.
What is that? I didn't hear that last one.
Interception.
Interception. Okay. Fair enough. Then
Land use.
land use. Okay. So we are getting. Then anything else?
Area of catchment.
Okay. Interesting. Area of catchment. Okay. Now, the very first. Okay. Anything else? Anything else that we've missed?
Depression storage.
Depression storage. Okay. So now depression storage. Okay. Anything else that anybody can think of? 3, 4, 5, 6, 7, 8. Eight things have come. Okay. So now this this very first thing that I wrote over here, rainfall. Can anybody maybe refine this further? I wrote rainfall. Can anybody refine it a little bit for me?
Rainfall intensity.
Very good. Rainfall intensity. Why did you say intensity, Raza? Right?
Certainly, the peak would depend on whether the intensity is more or not.
Okay. So now, okay. So you're saying rainfall intensity. Now, does rainfall intensity depend on something? Rainfall intensity doesn't depend on anything. So we'll leave rainfall intensity alone. Okay. Now, after having said this rainfall intensity, is there just one more thing that you think we need to take into account? One more parameter.
Location of those side drains in the whole campus.
Location of the side drains in the whole campus. See, wherever there's a road, there'll be a side drain.
Time of rainfall.
What do you mean by
Duration.
time of rainfall?
Duration of rainfall.
Yeah, duration.
Duration of rainfall. Okay. So you're all getting to the point. Yeah.
So you're saying cumulative rainfall.
You mean the cumulative rainfall? Okay. So let us say I have a rainfall intensity of 10 centimeters per hour. Okay, but it only lasts for 2 minutes, and then the rainfall intensity becomes 1 centimeter per hour. Okay. So am I interested in that 1 minute of 10 centimeters per hour rainfall intensity or not? Suppose I collect. Suppose I set up a rainfall monitoring gauge on this campus. Okay, and then I'm collecting information about rainfall intensity, and suppose my data tells me that at this particular location on some day it received 10 centimeters per hour of rainfall. The intensity was 10 centimeters per hour, but it only lasted for 2 minutes. Okay, does that 2 minutes of rainfall duration, does that matter here or does it not matter?
Not much.
So then what
If we are
matters?
talking about a day or something like that, then we'll consider the overall rainfall intensity.
Okay, so
Or
then what?
probably something like that's for a duration, like long duration.
Yeah. So what duration should we consider?
Longest distance.
What is that?
Some distance. Yeah, that one.
You're there. You just don't have the right word.
Yes.
Doesn't matter. The concept is there.
Greater than ponding time.
Bonding time. See now, remember this. Within your 500 acres or whatever your campus is, you may have different kinds of soil, right? If I have sand in one location, I'll have a longer ponding time. If I have clay in another location, I'll have a shorter ponding time. That does play a role in runoff. I'm not denying that. Okay, it does play a role, but which what's his name? Chakradhar was hinting at it. Anybody is able to tell me which duration we should look at?
Time of concentration.
Time of concentration.
Good. So now, this you need time of concentration. Okay. So these many factors are required for you to be able to estimate the peak runoff. Okay. So what kind of data do you need? You have the precipitation data. What other data will you require for this college campus of yours? Okay, maybe I'll give you some more information. So you already have precipitation data from 2018. I think I shared that data with you. And then I'm going to also share land use data for the whole state of Andhra Pradesh. Okay. What else? Anything else you need?
The slope of the campus.
Slope of the campus. So what I will do is I will give you topography.
Yeah.
So topography means the variation of the land surface over space. Okay. So for this, what we typically use is called a digital elevation model. Okay, it's called a DEM. Some people say DEM, some people say DEM, same thing. Okay, digital elevation model, which what I'm going to share with you has a resolution of 90 meters. 90-meter resolution means that it will give you one value for every 90 square meters. Sorry, not 90 by 90 square meters, not 90 square meters. The pixels, so it's basically a file which will have pixels, just like in your photo you have pixels, right? So here the size of the pixel will be 90 by 90 meters approximately. Okay, so about how much is that? Yeah, so it will give you the elevation every 90 meters, right? So over 500 and so many acres, you will have a number of points, a lot of points you will have. Okay, so you will have precipitation data, you will have land use data, you will have topography data. What I'm expecting you to do is to use all of this information and come up with this peak runoff. Okay, so if you remember this peak runoff, what is the formula we can use for this? What is the formula that we can use for this?
ICU.
Yeah, CIA, ICA, whatever you want to say. CIA. A is the area of your catchment. In this case, it's your college campus. We are assuming that any rainfall that falls outside the campus is not entering our campus. Okay, we'll assume that our campus itself is its own watershed. Okay, it may not be accurate. So, for example, in our campus, in our permanent campus at IIT Tirupati, what has been done is that since we are at the foothills of the mountain, whatever rainfall falls on the mountain will actually flow into our campus, right? So when it flows into our campus, we've actually kept gaps in the compound wall. All around the campus, we have the compound wall, right, or the boundary wall. So at some locations where there's a natural stream, we have left a gap under the wall so that the water can flow in. If you try to obstruct that water, it will keep put pressure on your wall and your wall may overturn and so on. So therefore, we have allowed the water to go through, right? Whenever you don't want an unnecessary stresses to build up on some structure, you allow that structure to not try to withstand the force applied by force of nature, whether it is wind or whatever. You allow it to be flexible. So it will, if you sway in the wind, you will not be uprooted. If you try to resist it, you will get uprooted by the wind, right? So anyway, so that's the thing. So in this particular case, for the sake of simplicity, we'll assume that the area of the watershed is the area of the campus, right? 550 acres or whatever your campus size is. This runoff coefficient, you will estimate. How will you estimate runoff coefficient? You are going to be given the land use data, right? Now remember, when you before you build the campus, your campus will have a certain kind of land use, right? Once you start building the campus, more and more buildings will come up, so you will lose some of the, maybe there may be some kind of some trees in that area. Those trees will move away, and then you will replace that impervious, sorry, the natural ground you'll replace it with impervious surfaces like concrete and so on. So therefore, to some extent, your runoff coefficient will increase, right? So in the case of IIT Tirupati, for example, what we are doing is all the construction that is going to happen on the campus is going to happen within 30% of the overall campus size, right? So out of those 550 acres, you're not going to build everywhere over all of those 500 acres. We will have lots of open spaces. We'll have green cover and so on. So you can assume something similar, right? You can assume that only 30% of it is going to become impervious surfaces. The rest of it will be whatever is currently existing, right? So then appropriately you can find out the runoff coefficient, and then you know how to compute the effective runoff coefficient. It is simply a arithmetic weighted arithmetic mean, right? Then comes this rainfall intensity I. This is the peak rainfall intensity occurring over a duration equal to
Time of concentration.
time of concentration. So once you reach time of concentration, if the rainfall intensity does not change, your peak flow also doesn't change, right? So you will have to find out what the time of concentration in your campus is, given the kind of location. So see, in this particular campus that we are in, it happens to be an area where the the slope is pretty high, right? So different parts of the campus, you've already seen the campus, right? You know that if you go from one part of the campus to the other part, there's a difference in elevation of almost 50-60 meters. 50 meters, can you imagine that? Huge difference in elevation. Not everywhere will have that kind of difference in elevation within the campus, right? So depending on that, the slope of the campus will change. If the slope changes, the time of concentration changes, and so on, right? So if the time of concentration changes, how will you find out the rainfall intensity? You have the precipitation data, right? So let us say in 2018, you have precipitation data. Let us say the time of concentration for your campus is, I'm just giving some number, is 1 hour. If the time of concentration is 1 hour, then you take the daily rainfall that you received in 2018. Okay, let us say on August 10th, 2018, you received 15 centimeters of rainfall. Okay, assume that it happened in 1 hour. It's a very, very extreme thing. Okay, this is the worst case possible, that you receive 15 centimeters of rainfall in 1 hour. That's a massive rainfall event. Okay, almost unlikely to happen. But just for the sake of calculating it, you just try to calculate it and see what flow rate you get. Okay, using that rainfall intensity. Okay, then we can appropriately adjust it, right? So this is the kind of approach that I'm expecting for this this project, right? Any questions? I'll take you to QGIS quickly, and I'll show you the data that I'm going to share with you. All the details will be present in the data. Okay. Any questions? Okay. So let me take you to QGIS. Share screen. Are you able to see QGIS?
Yes.
Sir.
Okay, so let me first, so on this left hand side on my screen, different QGIS environment will look a little bit different. You can move this, okay? You can move it and keep it here. I like to have it on the left hand side, so it's not a big deal. So here I'm going to add, I'm going to show add the data to you and show what this data means. Okay, I'm going to add raster layer. Okay, so here you go. So this is my, so for project 3 I've created this folder. So this is my land use, land cover data for the whole state of Andhra Pradesh. This is undivided Andhra Pradesh, okay? But you only have data for divided Andhra Pradesh. So please select a district in divided Andhra Pradesh, or if you are able to get access to data for your Nalgonda or Mahbub Nagar or whatever in Telangana, you can use that, no issues, right? So this is the land use data. Are you able to see the different colors? So these different colors correspond to different kinds of land use. So if you remember over here, there is this there's a accompanying legend which tells you what these different colors mean. Okay, maybe, yeah, I can't open it here, unfortunately. Yeah, it's not visible. It's just a image, okay, so it will not be visible. Forget it. But I'll send that file to you so you can.
Sir, which year's LUS is this, sir?
This is 2016-17. Okay, so this dark green that you see, those are forests. Okay, and then this background yellowish color that you see, that mostly yellow and light green and so on, those are all agricultural land. So that will be shared with you. Okay, don't worry about it. This, wherever you see red, do you see red over here? Those are basically cities. So this is a city. Okay, wherever you see red, that's a city. So over here, if you zoom in, this is Tirupati city. This is the forest right behind Tirupati in Tirumala, and this again you see a piece of red, that is Tirumala. Okay, so this is probably Yerpedu or whatever, and this is Kalahasti and so on. Okay, anyway, so these different colors correspond to these different types of land use. Okay, so then let me zoom back out. Okay, so this is the land use, land cover, and then the next data that I'll add is the DEM. Okay, I'm going to share the DEM for the entire state of Andhra Pradesh, but right now I have one piece of the DEM. It's basically a .tif file. Okay, if you open this .tif tif file, this one is for it's this western part of Anantapur district. So here I'll just zoom in over here. Okay, so this corresponds to the region in Anantapur district. So it's basically a square block. So within this, I have pixels of size 90 meter each. Okay, so these different colors correspond to different elevations. Okay, so now let me show you very quickly. I want you to create a college campus inside this. Okay, so let me zoom in a little bit. I'll zoom in. Okay, so let us say I want to create a college campus. I go over here. I say layer, create layer. Say new shapefile layer. So I'm going to create a polygon. I'm going to create a polygon shapefile. Okay, which will just get okay. Don't worry about this. This is very easy. Okay, project 3. You're still able to see me, right? Okay, so we'll create a file called college campus.shp. Okay, so I've created one. Then I'm going to edit this. Okay, I think I'm a little bit running out of time now. So let me quickly do it. I'm just drawing some shape. Okay. Okay, I think I missed it. Okay, so I've created this college campus over here. Okay, so if you want to find out the area of this college campus, you can click and find the area of the campus. So the area of this campus, I've just drawn some random thing. It's 15.9 hectares or 16 hectares. Okay, you can convert it to whatever appropriate units you want. And then within this, you can click on the digital elevation model and try to find out what the elevations are and so on. Okay. So the second file that you have over here, this one is the DEM, digital elevation model. This gives you the elevation above mean sea level. Okay. And then this other one that I have, this gives you the type of land use. So you can find out what land use is there within your college campus. This college campus, I just drawn it randomly somewhere. Don't draw it in the middle of a city. Okay. Within an existing city, you can't build a campus. Okay. So you'll just have to draw it somewhere where the land use is not red. Okay. I've just drawn it somewhere randomly over here. You can do the same thing and estimate your peak runoff for this campus. Okay. Make sure you make it of a size that is comparable to our campus, right? Don't make it a 100-acre campus or a 10,000-acre campus. Make it 500, 600 acres. I don't mind, as long as it is somewhere around that. It's okay. Okay. So that is as far as the project is concerned. One more note is that tomorrow I'm not available. I'm traveling tomorrow. So tomorrow's class will not have in the morning. We have the class from 11 to 12. So I'm going to tell you that we are going to have a surprise test tomorrow. So please inform everybody in the class so that you don't miss the exam tomorrow. So although I'm calling it a surprise test, it will not be a surprise. So please be available at 2 o'clock and make sure you tell all of your classmates so that nobody misses out on this exam. So it's the 5th surprise quiz. It'll be for probably 15-20 minutes duration. Nothing very difficult. Okay, as usual, you may have to take a photo of it and just upload it of your solution. Make sure your solution is legible and visible to me so that it's easy to create it and so on. All right, so we'll make up for tomorrow's missed class next week. Next Tuesday we'll take both the morning and afternoon classes, and then that will make up for the missed lesson tomorrow. Okay, so thank you very much, and if you have questions on this project, we'll discuss it maybe next time we meet on Thursday. Maybe I can do it a little bit slowly. This QGIS portion, I'll do it a little bit slowly. It's not very difficult. You are already familiar with it. It's just a question of understanding some more aspects of using QGIS. All right. So next class we will probably discuss this project a little bit and then move on to the next topic. All right. So thank you very much and take care, guys. See you on Thursday. And please remember, there's going to be a surprise quiz tomorrow at 2 o'clock in the afternoon. Make sure you convey this to all your classmates. Okay. Thank you very much. See you guys on Thursday.